Two steel jaws with 50 cubic yards between them drop through 150 feet of dark water on nothing but wire rope, and the sand they land in will hold on to them. Great Lakes Dredge and Dock runs two machines built for exactly that, the GL54 and the number 58, each rigged to buckets as large as 50 cubic yards, a single bite the size of a two-car garage, dug from 150 feet down. The crane swinging that load has no engine underneath it. It stands on a barge held up on steel legs driven into the harbor bottom, and every pound it tears off the seabed has to come back up through the water and swing out past the side of a floating hull, across a deck with 6 people on it and open water on 4 sides. That grip is physics. Dense, saturated sand cannot be sheared without expanding first, and underwater the water cannot flow into that opening space fast enough, so the pressure inside the sand drops below the pressure around it, and the difference pulls down on the closing jaws at the moment they need to lift. The largest grab dredger ever built carries 3 separate buckets for one crane. In ordinary seabed, it swings 200 cubic meters of bucket weighing 370 tons. In the hardest ground it is rated for, the bucket holds just over half that volume and weighs 480 tons, against a hoist limit of 690 that does not move. Harder ground, smaller bucket, heavier machine, less coming up each time. If you enjoy these documentaries, then subscribe. Thank you. Now back to the gritty history. A harbor is only ever as deep as its shallowest point, and for a working port, that number never stays still. Ships kept growing, drafts kept increasing, and the difference between a channel that could take them and a channel that could not sat on the bottom, underwater, where nobody could stand, no wheel could grip, and no crane boom fixed to a barge deck could reach far enough down to fix. For a long time, the answer to that problem was human labor pushed as far as it could go, men working in cofferdams, bucket ladders lifting a slow chain of small scoops up an inclined frame, and dipper dredges that dug the way a steam shovel digs, with a rigid arm on a fixed pivot, strong close to the machine and useless past the reach of that arm. None of it solved the real limit, which was depth. A rigid arm can only reach as far as it is long, and no amount of added power changes that. The grab dredge solved the problem by giving up the arm entirely. Instead of a fixed boom forcing a bucket through the ground, the digging tool was hung from a crane on wire rope, and depth stopped being a question of how long an arm could be built and became a question of how much rope could be spooled onto a drum. The cycle that does the work runs in 6 steps every time. Position the crane over the spot, lower the open bucket to the bottom, close it, raise it clear of the water, swing it over to a barge or hopper waiting alongside, and empty it. Then swing back and do it again, cycle after cycle, for as long as the job runs. The crane itself sits on a barge that, in most cases, has no engine of its own. It holds its position on spuds, heavy steel legs driven straight down into the bed, and a dredge standing on 3 spuds can walk itself forward a few feet at a time without a single tug standing by, or it can sit at anchor instead. The material it lifts does not travel far under its own power either. It gets swung sideways and dropped into a scow or hopper tied up alongside, and once that scow is full, it gets towed away and an empty one takes its place. Running that whole spread takes a crew of 6, a crane operator working the controls, a foreman, 2 laborers, an oiler keeping the machinery fed, and an equipment operator. 6 people, standing on a working platform with open water on every side of them, watching a loaded bucket cross the deck on every cycle and trusting the rigging that carries it. The idea itself is not new. 19th century engineers were already building double chain grabs and a single chain design called the hone grab, fitted with a hydraulic brake so the load came down under control instead of dropping loose. Those early grabs ran from about 300 weight up to more than 40 hundredweight, with a common working size holding about 1 ton of material per bite. A typical Kingston-type outfit of the period, engine, boiler, and grab together, weighed about 17 tons and sat on a platform 5 feet by 6. Its safe lifting height ran to about 20 feet above deck, which worked out to roughly 14 feet of usable digging depth below the waterline, burning about 90 pounds of coal an hour to do it, close to 2 pounds of coal for every ton it lifted clear of the bottom. At that 20-foot depth, one of those early machines could manage about 50 lifts an hour, close to 40 tons an hour in ordinary ground, and about 500 tons across a 10-hour working day. A current running faster than 5 or 6 knots was enough to throw the whole cycle off. American manufacturing caught up to the idea early in the next century. The Owen Bucket Company opened in Cleveland, Ohio in 1908, and the businesses that grew up around it and alongside it would spend the rest of the century building the buckets that hung off cranes like these. What none of that changed, then or later, was the one weakness built into the design from the very first grab that ever closed underwater. Hanging the bucket from rope is what gives a clamshell dredge its depth. It is also what takes away its downforce entirely. A rigid arm can be driven into the ground by a machine pushing on it. A bucket on a rope cannot be pushed at all. It can only fall, and it can only dig with whatever weight it happens to be carrying when it lands. That single fact, that the bucket can only dig with its own weight, is the whole argument underneath everything a clamshell dredge does. The sequence starts with the bucket wide open and the hoisting wire run out slack, so that as it drops, nothing is holding it back and nothing is pushing it down beyond its own mass. Research into the mechanics of the bite, carried out on clamshell dredges working in water-saturated sand, found exactly that. The grab penetrates the ground first by weight alone, before the crane does anything else to it. Only after it has settled into the bottom does the second wire, the closing wire, take over, hauling the upper and lower sheave blocks together and forcing the two jaws shut through the material underneath them. That same research found that the forces working against the side edges of the bucket as it closes are on the same order as the forces doing the actual cutting, large enough that they cannot be treated as a rounding error in the design. In loose or soft ground, that is more or less the end of the story. In dense, saturated sand, it is where the real fight starts. Sand packed that tightly cannot be sheared without its grains shifting apart from each other first, which means the sand has to expand slightly to let the jaws pass through it. Underwater, that expansion opens tiny pore spaces between the grains faster than water can flow in to fill them, and for a moment, the water pressure inside that sand drops below the pressure around it. That pressure difference acts like suction, holding the sand together, and it pulls back against the closing jaws, hard enough to hold the bucket down at exactly the moment it needs to come back up. It is the reason a grab that closes through soft mud without much resistance can stall and strain in dense sand that looks, from the deck, like it should be the easier ground to work. Broken rock is worse again, and the evidence for how much worse sits in how much material ends up inside the bucket when it surfaces. Engineering studies on clamshell production describe a fill factor for each type of ground, a simple ratio of how much of the bucket's rated volume comes up full on a given bite. In mud, that figure runs to about 72.5% of capacity, bite after bite. In broken rock, it collapses to about 10%. A 50 cubic yard bucket working broken rock comes up roughly 1/10 full, meaning the crane spends the same time, the same wire, and the same wear on the same sheaves to lift a fraction of the material it lifts in softer ground. The only way to make up that shortfall is to make the bucket itself heavier, so that what little rock it does close on gets forced in rather than pushed aside, which starts the same argument all over again. To dig harder ground, add weight. The weight is the one thing the machine also has to lift, swing, stop, and lower, on every single cycle, all day. None of this is theoretical for the people standing on the deck while it happens. Those 6 people spend the shift on a platform with open water on 4 sides and a loaded bucket crossing the deck every cycle, and a scow tied up alongside that has to be swapped for an empty one the moment it fills. Even away from the crane itself, that water does not forgive carelessness. At a 70-acre dredge lake in Irwindale, California, worked by a pair of 20 cubic yard clamshell buckets pulling material from depths of up to 95 feet. A mine safety investigation into a Vulcan Materials subsidiary's operation recorded how ordinary the trigger could be. On November 9, 2001, a foreman, Kirk Herrick, sent two workers, John Garcia and Clay Hall, to hose spillage from under a conveyor near the water's edge. Hall stumbled and fell in. Garcia went in after him. Neither man was wearing an available life jacket, and Garcia was not a strong swimmer. His wet clothing added weight against him, and divers recovered his body hours later in about 40 feet of water. The investigation afterward found no fault in the machinery at all, only in a task nobody had assessed as a hazard before it was assigned, and open water was already within a step of where the men were standing. Weight being the whole argument is also the reason the buckets kept getting bigger. American manufacturing followed that logic for most of a century. That Cleveland company was followed by a Williams bucket division that grew out of the Atlas Car Manufacturing Company, also in Cleveland, and by newer builders further south. Yon Welding and Dragline Buckets in Baton Rouge from 1946, and a Louisiana rebuilder called Hawco that started work in 1968 and eventually became a manufacturer in its own right, adding hydraulic and electro-hydraulic bucket designs in the middle of the 1980s. By the time those companies had spent decades building bigger and heavier buckets for bigger and heavier cranes, the numbers involved had stopped being intuitive at all. Consider what 50 cubic yards of steel weighs empty before it has closed on anything. During the deepening of Boston Harbor's outer channels, the contracting joint venture ran two buckets rated at 33 cubic yards each, and those two buckets, empty, weighed 80,000 pounds apiece. 40 tons of steel doing nothing but hanging on the wire before it had bitten into a single scoop of mud. That is what a bucket smaller than the ones in this story weighs with nothing inside it at all. Great Lakes Dredge and Dock runs the machines carrying the title's 50-yard buckets today. The GL-54 swings a bucket rated from 12 up to 50 cubic yards and digs to a depth of 150 feet, on a hull 185 feet long and 60 feet wide, drawing 8 feet of water itself. The number 58 carries a bucket rated from 20 up to 50 cubic yards, on a wider, shorter hull, 140 feet long and 72 feet across, and while its full reach also runs to 150 feet, working on its own spuds without outside support, it can dig to 78 feet. A third mechanical dredge in the same fleet, the New York, works smaller, 12 to 25 cubic yards to a depth of 75 feet, which is enough on its own to show how far the 50-yard machines sit above the rest of the working fleet around them. Cashman Dredging's Dale Pyatt sits above even that. Company records call it the largest clamshell dredge in the Western Hemisphere, a 1,200-ton hull, 180 feet long and 65 feet wide, carrying a bucket rated from 28 up to 60 cubic yards. Its crane carries a manufacturer's duty rating built to run one full load cycle every minute, 5,000 hours a year, for 20 years. A duty cycle that works out to roughly 300,000 full load cycles a year and something close to 6 million loaded cycles across its design life. It runs diesel-electric with joystick control, meets the strictest federal emissions standard in the country, and was, at the time it entered service, the only fully compliant dredge in the United States, and its double-walled fuel tanks hold close to a month's worth of fuel. It was the first entirely new dredge crane built in the industry in more than 20 years, its hull assembled at a shipyard on Staten Island, New York, and its crane installed at Cashman's own yard in Quincy, Massachusetts, by a crew of more than 30 people before it went to work for the first time in October of 2013. Cashman runs two other clamshell dredges alongside it, a smaller Icarus rated from 12 to 30 cubic yards, and a wood one rated at 14. Even the Dale Pyatt is not the largest grab dredger built anywhere in the world. That machine, named Gosho, was built in Japan in the year 2000 and is registered out of Nagoya. Its hull runs 100 meters long, 36 meters across, and 6 meters deep, drawing 3.5 meters of water, but its overall height, with the crane rigged, stands close to 50 meters, and the vessel displaces 7,052 gross tons. Its crane can hoist up to 690 tons and reach out to a working radius of 31 meters, and it can dig down to 48 meters below the surface, powered by 3 main generators of 2,795 kilowatts each, plus a smaller auxiliary unit, held in place by 2 spuds, each 1.6 meters across and 45 meters long. It has worked on the land reclamation project at Tuas, the new megaport being built in Singapore, and it is Gosho's own bucket table that carries the argument from the hook through to its full weight. In normal seabed, its bucket handles 200 cubic meters and weighs 370 tons. In hard ground, the bucket shrinks to 136 cubic meters, but the weight climbs to 400 tons. In the hardest ground it is rated for, the bucket holds only 106 cubic meters, less than half its soft ground volume, while the steel around that smaller volume weighs 480 tons, closing in on the crane's own 690-ton hoist limit with every degree the ground hardens under it. What justified building cranes this large was never the machine for its own sake. It was what a hanging bucket could reach that nothing else could. At Hell Gate, on New York's East River, the channel into the harbor was blocked for generations by underwater reefs. Engineers under General John Newton tunneled beneath one of them, Hallett's Point Reef, driving 10 headings and drilling 7,000 holes for close to 30,000 pounds of explosive, fired on September 24, 1876, at 2:30 in the afternoon, throwing spray and gas 123 feet into the air. The blast broke the reef apart, but broken rock on a riverbed is still rock in the way of a ship's keel, and it took the Atlantic Dredging Company until 1882 to lift 90,588 gross tons of shattered stone off that bottom and deepen the channel to 26 feet. The record credits the company with that tonnage and that depth, not with a named tool, and lifting shattered rock off a riverbed is exactly the work a hanging bucket is built for. 9 years later came Flood Rock, a reef so shallow that only 230 square feet of it ever broke the surface, so the engineers went underneath it entirely. A 70-foot shaft, 23 headings running north to south, 46 galleries spaced 25 feet apart, 4 miles of tunnel in total, 15,000 holes drilled and packed with close to 280,000 pounds of the explosive Rack A rock, plus another 5,000 pounds of dynamite, wired into 50,000 charges, of which only 3,000 carried a wire at all. It was fired on October 10, 1885, at 11:13 and 50 seconds in the morning by Mary Newton, the general's daughter. 9 acres of river surface lifted into the air, rock and foam climbing 150 feet. In front of a crowd, the record puts at 50,000 spectators. The record does not say what kind or size of bucket went in afterward to clear what the blast left behind, only that the broken rock still had to be lifted off the bottom before ships could use the channel, which is exactly the job a hanging bucket was built to do. Once the channel was open, trade through it ran to roughly $4 million of cargo a day. Blasting worked at Hell Gate because the rock there could be reached from tunnels driven underneath it. At the San Francisco-Oakland Bay Bridge, started in July of 1933 and finished in January of 1937, the rock the piers needed to stand on was under open water, and the only way down to it was straight through the mud above it. Of the bridge's 51 piers, 26 were major structures, and 8 of those were built on submerged foundations at depths the engineering literature of the time called beyond all previous records, pier foundations reaching as deep as 235 feet below the surface, with a base footprint on the largest piers of 92 feet by 127. The central anchorage was built as a caisson roughly 100 feet by 200 feet in cross-section, floated into place on compressed air, and sunk through 55 separate vertical shafts, each 15 feet across, cut straight through the structure. Buckets were dropped through those cylindrical openings to dig the mud out from underneath, all the way down to bedrock, one shaft at a time, so the caisson could settle onto solid ground instead of sitting on silt. Even by the standards of that project, it was an extreme case. The south pier of the neighboring Golden Gate Bridge went down only about 100 feet below sea level on a 90 by 180-foot base, and its north pier reached only 20 feet down. The Bay Bridge's deepest foundations went more than twice as far into the dark. 80 years later, the same tool was still opening the same kind of bottleneck at industrial scale. Boston Harbor's Deep Draft Navigation Project, its second phase, moved about 12 million cubic yards of silt, Boston blue clay, glacial till and weathered rock out of the harbor's shipping lanes, deepening the outer harbor channel from 40 feet to 51 and the main shipping and reserve channels from 40 feet to 47 across a stretch of channel 7 miles long, working around the clock every day of the year, from July of 2018 to January of 2021, finishing nearly a year ahead of schedule. The Dale Pyatt worked that job alongside two other clamshell dredges, the F.J. Bellissimo and the Paula Lee, a backhoe dredge called the Captain A.J. Fournier, and a ripper barge the contractor built in-house. 7 split hull scows carried the dredged material 20 nautical miles out to the Massachusetts Bay disposal site, fitted with a proprietary geofence system built to stop a scow's hull from opening by accident during loading or the tow-out. What that channel work bought the port was capacity, the ability to take container ships carrying 12 to 14,000 containers, up from 10,000 before the project began. Not every obstruction in a channel can be dredged around, and Kill Van Kull, the strait between Staten Island and New Jersey, proved it. During a deepening contract there that ran from August of 2003 to October of 2004, with rock removal concentrated between May and August of 2004 on a contract worth $35.5 million, crews cutting a mile of that 1,000-foot wide channel down to 45 feet, plus a foot and a half of overdepth, hit an unexpected deposit of diabase rock, limestone, and shale. Drilling and blasting it loose would have meant closing one of the busiest waterways in the country, so instead, the Dredge S. Comoletti was fitted with a hydraulic hammer, an IHC unit rated to work at depths to 65 feet, a self-contained 37-foot, 14-ton machine that could operate fully underwater without losing its striking energy to the water around it, breaking the rock in place so the buckets could keep lifting it out without ever shutting the channel down. The last major deepening contract on Kill Van Kull, taking it to 50 feet, was finished on September 24, 2011, opening the port to the largest ships afloat. None of that work happens for free, and the economics of a clamshell spread explain almost as much about how the machine survives as the physics of the bite does. A typical clamshell dredge costs somewhere around $14.5 million to build, carrying on average about 2,038 horsepower of installed power and a hopper capacity around 3,440 cubic meters. Running it day-to-day adds maintenance costs that, on a $14.5 million dredge, run to roughly $2,000 to $4,000 a day before fuel, before crew, before insurance, and insurance itself runs about 2.5% of the dredge's value every year it stays in service. None of that spending stops because the ground underneath the bucket gets harder to dig. What a cubic yard of dredged material costs to move swings enormously depending on where and what it is. At Barcelona Harbor, unit costs ran to about $8.46 a cubic yard. At Erie Harbor, closer to $3.47. Across large projects generally, contractors work to a rough band of $2 to $5 a cubic yard, and real winning bids show how much of that money goes to work that has nothing to do with digging at all. The Erie Harbor contract awarded in 2014, moving 191,139 cubic meters to a depth of 7.6 meters, went for $868,980. The Coos Bay upriver contract awarded the following year, moving 198,784 cubic meters to a depth of 10.7 meters, went for $2,862,160, and a full quarter of that figure went to moving the dredging spread to the site and back again, before a single cubic yard of material had been removed. At Suisun Bay that same year, moving 133,797 cubic meters to the same 10.7-meter depth, on a contract worth $1,769,330, the mobilization and demobilization cost alone ran to 45% of the entire bid. Nearly half of everything spent on that job paid to move the equipment there and back, with none of it touching the ground. Under that kind of financial pressure, real-world production on a clamshell spread is planned around a derating from the theoretical maximum, engineers typically figuring on about 85% of nominal output once delays for advancing the dredge and swapping hoppers are accounted for. Every hour lost to a stuck bucket, a jammed sheave, or ground that will not fill the bucket properly is an hour the crew cannot get back, on equipment charged against the job, whether it is cutting or sitting idle. Standard American practice sizes the bucket to the size of the job, 6 cubic yards for work, under about 76,455 cubic meters, 10 cubic yards up to about 191,139, and 15 cubic yards above that figure, though modern practice on many jobs has settled on buckets closer to 10 to 15 cubic meters, roughly 13 to 20 cubic yards. Bigger buckets cost more to run and more to insure, so nobody rigs a 50-yard bucket to a job that a 10-yard bucket can clear on its own. And the ground itself, more than any number in a bid, sets whether the clamshell is even the right tool for a job at all. Industry guidance on dredging equipment describes the mechanical grab's production as moderate to low compared with the alternatives and flatly ineffective in fine silt, which tends to run straight back out of an open bucket before it ever clears the surface unless the bucket has been sealed against that kind of loss. It performs well in sand, clay, gravel, cobbles, and occasionally broken rock, and it earns its keep in places a hydraulic dredge cannot reach at all. Tight against a quay wall, working spot repairs in a busy harbor, or digging through moraine ground littered with large stones that would jam a cutter head or a suction pipe outright. That division of labor comes down to the same rope that gives the clamshell its reach in the first place. A hydraulic dredge is limited by how far its pump can push material through a pipeline, and that limit tightens with depth and distance. A mechanical clamshell is limited only by how much cable is on the drum, so for machines of comparable size, the clamshell keeps working in deep water long after a hydraulic dredge has run out of pipeline capacity to lift with. In open, clean, uniform sand, at ordinary depths, a cutter or hopper dredge will outproduce a clamshell every time. The clamshell survives on the ground nothing else can touch, and it pays for that ground on every single cycle. The hoisting wire and the closing wire both carry the full weight of a loaded bucket over the crane's sheaves each time the bucket comes up. Not once in a while, but on every bite, all day, in salt water that works against the steel the whole time. A crane built to the Dale Piatt's own duty rating, 1 full load cycle a minute, 5,000 hours a year, for 20 years, is asked to carry that same full load over those same sheaves close to 6 million times across its working life. And on every cycle, the brakes have to hold that same full load against gravity the moment the bucket stops moving. Every one of those cycles ends the same way physically, no matter what the ground gave up to get there. The load has to leave the center of the hull and travel outboard, out past the side of a structure that is floating, not standing on solid ground, and a floating structure resists that shift by tilting. The heavier the load, the further out it swings, and the narrower the barge underneath it, the more that tilt matters, and it matters most exactly when the bucket is fullest and furthest from the center line, on its way across the deck to the scow. That physics is not unique to a dredge, and a documented case from a construction site makes the point without a clamshell bucket anywhere near it. On November 4, 1996, at around 2 in the afternoon, on a bridge and cofferdam project in Nebraska, a crane mounted on a barge, not a dredge of any kind, but a pile-driving crane supporting bridge construction, was lifting a Birminghamer pile driver with 70-foot leads, a combined load of about 15,500 pounds, off the aft port side of the barge. The operator, 39 years old and 2 months into the job, rotated the load clockwise while lowering the boom, and as the load swung past the barge's starboard bow, the crane began to tip. Its left track lifted clear off the deck, and the crane went over on its side, into a pile installation machine on the same barge. The operator died in the cab of crushing chest injuries. At the boom angle he was working, about 52 degrees, the load chart allowed 10,550 pounds. He was lifting roughly 1.5 times that. The investigation afterward recommended never exceeding a load chart, securing cranes positively to the barges carrying them, and running documented spot inspections, recommendations aimed at any crane working from a floating platform, pile driver or dredge alike. A real clamshell dredge failed for closely related reasons 10 years later. On October 10, 2006, at a sand and gravel operation in Oxford, Michigan, dredge operator Mark Hickmott, 45 years old, took over the overnight shift at midnight aboard a floating clamshell dredge. At around 10 minutes to 5 in the morning, the lights on the vessel went out and the conveyor stopped running. A co-worker went to check and found the dredge capsized in about 115 feet of water. Hickmott's body was recovered that afternoon at 5:30. The cause of death was drowning. The investigation that followed found that roughly 8,290 pounds of steel reinforcement had been added to the deck beyond what the manufacturer specified, that 4 of the dredge's pontoon cells were leaking and being kept afloat only by sump pumps nobody could fully rely on, that oversized boulders were being stored on the open deck, adding still more weight in the wrong place, and that the high dredge alarm, the overload sensor meant to warn the crew before any of that mattered, had not been maintained at the setting the manufacturer specified. The investigators' own words were direct. The dredge had been modified and used beyond the design capacity the manufacturer intended. Not every failure of a floating dredge announces itself with a capsize in front of a crew. On January 16, 2023, on the Mississippi River, a non-propelled dredging vessel named the W.B. Wood capsized in the early morning with nobody aboard injured, but the mechanism behind it was the same slow accumulation of unwatched weight and unwatched water. A storage space on the starboard side had been flooding through an open through-hull pipe that was missing its overboard check valve, and once that space filled, the flooding spread through watertight bulkheads that had themselves been compromised. The crew had found water in that space 2 days before the capsize and had not been able to identify where it was coming from. Roughly 5,500 gallons of oil went into the river, and the vessel itself, valued at $1.5 million, was a total loss. The federal investigation that followed put it plainly. The company had no requirement for regularly checking the compartments below deck, and that gap in a simple, low-cost inspection routine was what let the flooding go undetected until the vessel was already lost. Nobody died on the W.B. Wood, and the failure there took days to build before the vessel went over. 8 years earlier, on a different dredge, the same kind of accumulation ran its course fast, and it took a man with it. Dryfork Sand and Gravel operated a floating sand dredge at its mine in Cleves, Ohio. A Rohr-built machine from 1993 fitted with an electro-hydraulic clamshell bucket. Described in the eventual investigation report by its working name, a grab, hung from a gantry crane with dual winch motors, and kept afloat on 5 pontoons divided into 20 separate watertight compartments, with overload sensors built into the system to keep the crane from lifting past what the hull and the rigging could safely carry. On June 30th, 2015, that clamshell bucket got stuck on the bottom, about 65 feet down. The manufacturer's own manual addressed exactly this situation, in language that left no room to interpret it differently. Breaking loose of a stuck grab was not allowed, and no hoisting above the permitted lifting capacity of the equipment was allowed either. A winch built to lift a working load could not be run harder to break a bucket free that the ground itself was holding onto, because the same underpressure that makes a bucket bite also makes it grip when something goes wrong at the bottom. The crew found another way. On July 2nd, and again on July 10th, they worked through an unauthorized recovery procedure of their own devising. Flood the dredge's own pontoons with water, so the whole vessel settled lower, and the hoist cables came up tight against the stuck bucket, without the winch motors having to do the lifting themselves. Then clamp the winch brakes shut, not with any factory mechanism, but with plain steel C-clamps, locking the cable in place under that tension. Then pump the flooded water back out of the pontoons, so the hull's own returning buoyancy, the whole weight of a dredge trying to rise back to its normal draft, did the work of pulling the stuck bucket free instead of the winch. On July 2nd, it worked. 3 things stood in the gap behind that improvised fix, and none of them were visible from the deck while the crew worked. The overload sensors that should have registered a load beyond safe limits had been intentionally removed by management at some point before that summer, so nothing in the system was positioned to object. The pontoon access hatches, meant to be sealed to keep those 20 compartments watertight, had been left unfastened, and the workers running the recovery had never been given task-specific training in how to free a stuck bucket safely, because there was no sanctioned procedure for it at all, only the manual's flat prohibition and whatever the crew had worked out for themselves in its place. On July 10th, at about 11:15 in the morning, the crew went back to the same procedure after returning from lunch. Crew member Robert Cooley noticed water covering the deck. The dredge began to list more and more severely, and then came a very loud bang, later identified as a conveyor cable breaking under load. The vessel rolled and capsized in roughly 40 feet of water. Cooley, wearing a life jacket, was thrown overboard and swam to shore. William Roll, the mine's 50-year-old superintendent, did not come up. He disappeared into the vessel as it went over. Divers recovered his body 8 days later, inside the motor control center room, deep in the submerged structure of the dredge he had helped run. The investigation into his death, carried out by federal mine safety investigators, laid out its root causes without much room for ambiguity. The dredge had been used beyond the design capacity the manufacturer intended, in direct contradiction of the plain warning already printed in its own manual. Management had intentionally removed safety-critical overload sensors that existed for exactly this kind of situation. The pontoon hatches that should have kept the hull's watertight compartments sealed had been left open, and the crew asked to free a stuck bucket 65 feet down had never been trained for the job they were doing when the dredge went over. The machine built into every clamshell dredge since the very first hone grab exists to lift the bottom of a channel out of the water, one bite of its own weight at a time. At Dryfork, that same machine, jammed into ground it could not release on its own, was made to lift against the bottom itself, using the entire buoyancy of the hull as the only force big enough to try. For one day, on July 2nd, the bottom let go. On July 10th, it did not, and the dredge that had been built to outlift the ground went under it instead. Nothing in the record suggests the industry ever tried to solve that limit by building bigger cranes without end. Gosho's own bucket table is the clearest evidence of why not. A 690-ton hoist and a 31-meter working radius are fixed numbers set by the steel and the machinery of the crane itself, and every additional ton of bucket weight needed to bite into harder ground eats directly into the margin left under that limit. That is the same trade the fill factor already showed in softer ground and in broken rock, where a bucket that comes up about 72.5% full in mud collapses to roughly 1/10 full once the ground turns to broken rock. Gosho's own numbers carry that shortfall all the way to the crane, since the extra steel needed to force a smaller bucket through harder ground counts against the same 690-ton hoist limit before any of the material inside that bucket adds weight of its own. And the volume coming up with each bite keeps shrinking the whole time. Weight buys the bite. It also spends the crane, cycle by cycle, and there is a ceiling on both sides of that trade that no amount of added engineering moves by itself. What the hanging bucket still does, nowhere else can. Duty cycle crawler cranes working from the surface of Lago di Luzzone removed 125,000 cubic meters of sediment from depths reaching 200 meters. A purpose-built deep-water excavation grab, rated for depths to 1,000 meters and deployed in this case at 150 meters on the White Rose oil field for Boscalis and Tideway, held its position with three-dimensional tracking and heave compensation and still managed 150 cubic meters an hour in stiff clay, accurate to within 20 centimeters, across a project that ran 13 months. In the port of New Bedford, Massachusetts, a fully enclosed environmental clamshell bucket, built to contain material that might carry industrial contaminants, removed 104,000 cubic yards from the federal channel to deepen it to 29 feet, holding what it lifted for 12 hours before it went to disposal, sealed the entire time, exactly because an open bucket cannot be trusted with material that has to stay where it is put. The GL-54 and the number 58 are still on the water today, rigged to buckets as large as 50 cubic yards, and they still dig to 150 feet. The seabed still gets ripped open the same way it always was, by weight dropped into water nobody can see through, closed on the strength of nothing but its own mass, and hauled back out one load at a time, by a crane bolted to a hull that has to stay afloat the whole time it works.